Okay, so I will start. Thank you so much for attending the fifth lecture. I hope everyone is doing well. Today we're going to visit chapter 6 on the issues of specification. This is going to be the first part of two discussions regarding issues of specification. So we're going to spend time this week as well as next week to talk about specification issues. Okay, so I think this is going to be an important tools that you have to understand and important concepts that you have to understand as well. And we're going to go through Stata examples as well, because I think it's good for everyone to know the technical implementation of the concepts using data. Okay, so I will start today's lecture on specification issues. So the outline for today is that we're going to discuss data scaling, we're going to discuss beta coefficients, we're going to discuss interaction terms, we're going to discuss polynomials and goodness of fit. At the end of the discussion today, I will spend time to discuss prediction and residual analysis, in particular confidence intervals for predictions, prediction interval, as well as residual analysis. So this is the agenda for today. And again, if you have any questions or if you have any thoughts, or if you feel that you're being left out in the discussion of the concepts, please unmute yourself and ask the questions. Okay, don't go to the next concept without really understanding the current concept, because they're usually interrelated. Okay, so without further ado, I'm going to start with the first issues of specification, which is on data scaling. Okay, the data sets for today's lecture are all taken from Jeffrey Wooldridge textbook. The first one is on the birth weight, the second one is on house price, and then the third one is on attendance. So you all have access to these data sets, and you can use them for exercises later on. Okay. All right, so let's start with the first one, which is on data scaling. So data scaling is basically an important technique that researchers use for presentation purposes. So for example, suppose that mean of earnings in the sample is 1,450,000 rupiah. And we regress the earnings on age and other covariates. Okay, so suppose we're interested in the estimated coefficient of age. Now the issue is that we're going to get estimated coefficient in the area of thousands. Okay, so there's a lot of zeros. We could also face the case where the dependent variable on the left-hand side is actually a relatively small number, and then you also have relatively large number on the right-hand side of the equation. So the estimated coefficient that we get from the OLS regression is going to be 0.000 and some numbers. Okay, it's going to be quite difficult to really understand the estimated coefficient. It could be that the estimated coefficient looks so small, although it's actually economically significant. We can also have the fact that the estimated coefficient is quite large, but they're not economically significant. And so what we like to do is we'd like to identify a strategy so that we can better present the estimated coefficient without changing anything essentials. So that's going to be the goal of data scaling. Okay, it's not super complicated. It's quite easy. It's quite straightforward, and then the consequences are traceable. Okay, so rescaling data is a common practice, especially if we deal with variables with relatively large nominals, for example, income. So instead of regressing income in millions of rupiah, we can actually regress income in thousands of rupiahs on the covariates. Okay, we can also regress incomes in terms of millions of rupiah on the covariates. Okay, so for example, in the previous slide, we showed that the average income in the data, or the average earning in the data, is about 1,450,000 rupiah. Okay, what we can do is that instead we can transform this variable by dividing it with 1,000. So we have 1,450. And so the unit will now be 1,450,000 rupiah. Okay. Alternatively, what we can do is we can actually transform this into millions. So we can divide 1,450,000 rupiah with a million, and we'll get something like 1.45 million. Okay. And so this is what's called data scaling. Again, it's quite straightforward. It's quite traceable. And what we need to know is whether using data scaling is going to change the estimated coefficient or not. Okay. That's one example. Another example is, suppose instead of regressing weight, in grams, we can instead regress it on kilogram, for example. Or if we need it on other units, it's also possible. So the simple rescaling is something that is quite convenient to do. Okay. Any questions up to this point regarding the concept of data scaling? Okay, so I'm assuming that everything is clear at this point. Again, if you have any questions, you can always unmute and then ask the questions. Okay. Now, the key question that we'd like to answer is that, does rescaling change the estimated coefficient? Okay. Okay. So suppose that we regress earnings on age. So this is the variable without the transformation. Okay. And then we regress it on age. Now, suppose that we divide the earnings by 1,000. Okay, so again, we divide the earnings by 1,000. Okay, what would happen to the estimated coefficients, the b hat, the beta hat j? Or in this case, what would happen to the beta hat 0, and what would happen to the beta hat 1? Okay, so if you recall, mathematics is going to be quite, straightforward. If you divide the left-hand side of the equation by 1,000, then to maintain the equality, you should also divide the right-hand side by 1,000. Okay, and so in this particular case, what is C? C is just 1,000. Okay, so we know that rescaling the data is going to change the estimated coefficient, beta hat 0 and beta 1 hat in this particular case. The next question is, what about the standard errors, the T statistics, the F statistics, and the confidence intervals? Will they change? Anyone has an opinion, or anyone has a guess whether the standard errors, the T statistics, the F statistics, and confidence intervals, will they change or will they stay the same? Anyone would like to have their say? Okay, Buyung, can you guess whether the standard errors or the T statistics, will they change or will they stay the same? Okay,
if I may, sir.
Yes, go ahead.
For the standard errors, I'm expecting that the numbers will change, in which it will be smaller as it is divided by 1,000. But for the T statistics, I'm guessing that it will be the same.
Okay, very good. So the estimated beta 1 is going to be divided by 1,000, and the standard errors will also be divided by 1,000. So basically, it's gonna be the same T statistics. Okay. Any thoughts on the F statistics and the confidence intervals? I mean, if you can guess, since now the estimated coefficients have changed, the estimated standard errors have changed, then the confidence intervals will have to change as well. Okay. All right. I guess we can revisit Stata now, and I'll provide you with an illustration on data rescaling, and then how is it done. Okay, so I'm gonna share the Stata screen. Okay, so the data that I'm going to use today is the birth weight. Oops, the data is not. Let me use this instead. Okay. Okay. Let me find the data first. It should be around. Okay, so here goes the data. So let me pull up the variables that we have in the data. So we basically have family income, we have cigarette tax, we have cigarette price, we have birth weight. Birth weight is going to be our variable of interest. We have father education, we have mother education, and so on. Okay. Another variable of interest is going to be the number of cigarettes smoked per day during pregnancy. Okay. So what I'm going to do is I'm going to do a regression, okay, of birth weight and cigarettes as well as family income, okay? And then I'm going to use the robust standard error. This is to account for general heteroscedasticity, okay? And then after I do the regression, I have estimated coefficients for cigarettes as well as estimated coefficients for the family income. Okay, so suppose that we're interested in regression of birth weight, not in ounces, but actually in pounds. Okay, and so if you go to the conversion, you can look at it online. We can find that 1 pound is actually equal to 1/16 ounces. Okay, and so what we're going to do is we're going to rescale the left-hand side variable only. Okay, so instead of regressing it on the birth weight, what we're going to do is we're going to regress it on birth weight in pounds, and we're going to use basically the same right-hand side variables, the number of cigarettes smoked per day, as well as family income. And then we're going to use the robust heteroscedasticity, robust standard errors option. Okay, and then we do the regression. Now, as you can see, the estimated coefficient of the number of cigarettes smoked per day is different, okay, in the regression with birth weight in ounces and then birth weight in pounds. You can also see that the estimated coefficient of family income is different than the estimated family income in the regression with birth weight in pounds. What's interesting though is that the t-statistics, they don't change. So for example, the t-statistics for cigarettes smoked per day is still negative 5.22. And in the regression with birth weight in pounds, the estimated t-statistics is still negative 5.22. You can also find that the estimated t-statistics for family income as well as for the constants are the same. Okay. We can also see that the 95% confidence interval are different. This is quite straightforward because the estimated betas as well as their standard errors have changed due to the rescaling, and so the confidence interval also changes. Okay, what's interesting though is that the F statistics are actually the same. So the T statistics and the F statistics, they're not affected by the change. Okay, so just to conclude, suppose that we modify or we scale the left-hand side variable by a constant, say it could be any constant, say C, then the estimated coefficients on the right-hand side is also going to be divided by a factor of C. Okay, the standard errors are also going to be different by a factor of C as well. The T statistics, the F statistics, they're going to be the same, and the confidence interval will also change to reflect the fact that the estimated coefficients as well as their standard errors change. So that's a relatively straightforward way of identifying what would happen if you rescale the data, particularly the data on the left-hand side variable. Okay, all right. So I'm going to go back to the presentation, and we're going to discuss another way of actually rescaling. So here, what we're going to do is, instead of rescaling the variable on the left-hand side of the variable, we're actually going to rescale the explanatory variable. So in this particular case, instead of, say, regressing in terms of years, so age in terms of years, what I'm going to do is I'm going to regress age in terms of months. Okay, so recall that month is going to be the age reported by individual multiplied by 12. Okay, and so, you know, if we write the equation, we have earnings and then beta 0 hat and then beta 1 hat, and then we multiply age by 12. So to keep the equation constant, okay, or the equation unchanged, what should be the value of C? Anyone? So we'd like to know.
Sir?
Yes, go ahead.
Is it 1/12?
Yes, exactly. So to keep the equation unchanged, then C must be 1/12. Okay, so with this, you know, the scaling of the explanatory variable, then the estimated coefficient will change by kind of like the inverse of the change. Okay. Okay, any questions on the data rescaling, both for the dependent variable as well as for the explanatory variable? Okay, again, I'm going to quickly go back to Stata to provide you with an illustration of the rescaling. Okay, and so recall that in the first regression, what we did was that we regressed birth weight on the number of cigarettes smoked and then family income. So instead of regressing on the number of sticks, we want to regress it on the number of packs. Okay, and so we're going to basically you know, run the same model, but instead of regressing it on the number of sticks, we're going to regress it on the number of packs. Okay, and so let's do the regression. Okay, now in the first regression, the estimated coefficient for the number of cigarettes smoked is about -0.46. Now, after I convert it to packs, then the estimated coefficient is multiplied by around a factor of 20. So what's the idea? The idea is that to convert the number of cigarettes into packs, you need to divide the number of cigarettes by 20. Okay, and so if you divide the right-hand side of the equation by 20, and to keep the equation unchanged, you need to multiply the estimated coefficient by 20 as well. Okay, and so basically the number of packs here, the estimated coefficient for the number of packs is basically 20 times the estimated coefficient on the number of cigarettes smoked. Okay, of course, the standard errors are going to change as well. The 95% confidence interval will change. However, the T statistics as well as the F statistics, they don't change. Okay, so it's very, very interesting. Okay, in the Stata file that I shared in ELA, you will observe an example on how to do multiple estimations, okay, and then to produce a regression outputs in a table. Now for that, you need a command called eststo, and so what you can do is that if you don't have it in your laptop or your computer, you want to ask Stata to find it online, and then once you find it online, what you're going to do is just click on the example or the packages that appear in the Stata search, and then click on the link, and you'll have an option to install it. So click here to install it, and then Stata will guide you to the installation process, which is quite straightforward. You don't have to do anything basically. Okay, so what's the use of this eststo clear? So basically we can use the command to actually store estimates in the local, like the temporary hard drive, and then use that to present on table. And so I'm going to run several regressions here. Basically, I'm going to run regressions of birth weight on the number of cigarettes and family income. And model 1 is where I use the original variable, birth weight in ounces. The second model is the regression of birth weight in pounds on cigarettes and family income. And as you can see, the estimated coefficient is basically 1/16 of the estimated coefficient in the first model. In the third model, instead of regressing it on the number of cigarettes smoked per day, I regress it on the number of cigarette packs consumed per day during pregnancy. Okay, and the good thing about this command is that you can actually export it and then save it to Stata. So I have to change my directory, but you can do it, and then you can actually get output table on your Word. Okay, and so given this kind of like automation of estimation tables, then it's going to be quite straightforward for you to report regressions in the future. Okay, all right, so that's going to be on the topic of data scaling. So basically you have data scaling for the left-hand side variable, you have data scaling for the variable on the right-hand side of the equation, and you see that in general, the estimated coefficient as well as the standard errors will change. However, the t statistics and the f statistics will be the same. Okay, any questions or any thoughts before I continue and then discuss the next topic, which is data coefficient? Go ahead. All right, that's great. So I'm going to start the discussion of beta coefficients, and again, from time to time, I'm going to revisit Stata just to provide you with an illustration on how to do estimations and eventually how to interpret the estimated coefficients. Okay, we'll start with the beta coefficient. So basically, in many applications, researchers deal with variable which is hard to interpret. So for example, test scores. So tests change across years or across regions, and thus the distribution of scores. Okay, and so for example, if you recall, you entered the Faculty of Economics and Business having to do Gadjah Mada Scholastic Test, so GMST. So GMST changes from year to year. Okay, so basically the same test score of, say, I don't know, 520 in 2020 is going to be different with 520 in the year of 2019. Why? Because the problems could be different, and then the individuals who took the GMST test could be different. And so the difference could lead to different meaning of each number observed in the test score. Okay, and so if we have tests change across years or across regions, then it's not going to be straightforward to just run the regression of test scores on characteristic that we're interested in regression. Okay. Another thing is about scales. And so in a lot of data analysis and a lot of modeling, we're interested in some scales. So for example, religiosity scale, we're interested whether or not religiosity scale is correlated with, say, some behaviors. And we're also interested whether or not risk attitude, so whether or not an individual is risk averse or an individual is risk loving, is going to be correlated with some output. Okay, and so given this variance in the variables that we use in the regression, what is the best practice? Okay, and so another alternative is to ask what happens when the test score is one standard deviation higher. Okay, so instead of just running regression on the variable test score, we're going to do some adjustment. Okay, so the adjustment that we like to make is called standardization. Okay, so again, the adjustment that we like to make is called standardization. So if you recall from your statistics class, suppose that you have a random variable x, and x is normally distributed with a mean of mu and then standard deviation sigma. You can actually do a z transformation. Okay, so a z transformation is a transformation such that you subtract the random variable with the mean of mu and then divide it by the standard deviation. And then the z variable is going to be a normal distribution variable with a mean of 0 and a variance or a standard deviation of 1. So this is called the standardization. Okay, and we can actually do standardization for the variables in our regression. Okay, so for example, the xi tilde is a standardized variable of x. So basically, to get standardized x, we have to subtract x from the mean and then divide it by standard deviation. Okay. So by having this transformation, then the unit of the variable is actually going to be different as well. Okay, so the unit is now going to be standard deviation. Okay, so a unit observed in this variable is going to be a standard deviation. Okay, so that is standardization, and we're going to discuss what is the consequence that we're going to get if we do standardization on the regression model that we have. Okay, before I move on to the next slide, any clarification, any questions on this particular discussion? Okay, very well. I'm going to continue into the next slide. So let's start with the original equation. Okay, so this is going to be a very simple mathematical exercise. So I'm going to invite you to do it independently on your own. Again, it's not going to be that difficult. So let me give you the idea of the steps for the standardization. Okay, so we're going to start with the original OLS equation. And so basically, we're going to regress y on x1, x2, and so on until xk. Okay. From the regression, we're going to obtain the estimated coefficient beta 0 hat, beta 1 hat, beta 2 hat, beta k hat, and so on. So the next step that we'd like to do is we're going to take the average of the OLS equation. Okay. So basically, you take the average of y, and so if you take the average of y, then you get the average of the x's as well. Okay, as well as the factors that you do not observe, or the average residual. And if you recall from chapter 2, the average residual is just going to be 0. Okay. All right. After you do the mean, the next step that you like to do is subtract the original equation with the mean equation. Okay. And after you subtract it, then you're going to get the following. So yi minus y hat is going to be equal to beta 1 hat, x1 hat minus x1 bar, and then beta 2 hat multiplied by x12 minus x2 bar, and so on. Again, it's not going to be difficult to get from this point to this point. So you just have to write it down in the paper, and then you're all going to be set. Now, the next thing that I like to do is divide both sides by the standard deviation of y. Okay, so if we divide the standard deviation of y from the left-hand side, then we'll also have to divide it on the right-hand side. Okay, well, hold on. We don't have y on the right-hand side. So what should we do? Okay, that's something that for us to actually discuss after this. Okay, all right. We're going to do a very simple transformation. Again, the transformation is not going to be difficult, so bear with me for a little moment. So I'm going to take one particular example. Okay, and so I have beta 1 hat. Okay, and then I have the estimated, which is the estimated coefficient for this. And then I have x1 minus x1 bar. Okay. And then recall, I divide this by sigma y. So this is again just a portion of the equation that we saw in the previous slide. This is just going to provide you with that intuition. Okay. Now, what I'm going to do is just a simple trick. So if you divide something by a constant c and you multiply it the same equation, you multiply the same equation with c, then basically it's just the same equation. So what I'm going to do here, I'm going to multiply it by the standard deviation of x1 and then divide it by the standard deviation of x1 as well. Okay. All right. And so we can rearrange from this. Okay. And so after we rearrange, we have something like this. So we divide this by the sigma of x1, okay, and then we multiply it by sigma x1, okay. So what is this one? So this one is actually the standardized x1, okay. And what about this one? So this part is what's called the standardized coefficient or the beta coefficient, okay. And so this is what we're interested in, okay. So one thing that needs to be clear is that in this regression, we don't have a constant, okay? Why don't we have a constant? Again, you can go back to the previous slide. And then from that previous slide, you can see that from the original equation, and then you subtract it to the mean equation, the beta 0 is going to fall off, okay? So basically it's going to be eliminated. And so this is called the beta coefficient. And so what we're interested in is how do we interpret the estimated coefficient? Okay. So basically, since the left-hand side is transformed into a standardized variable and the right-hand side variables are also transformed into a standardized variables, and the estimated coefficient is going to be the following. So if x1 increases by 1 standard deviation, then y is going to change by beta 1 standard deviation. So the unit of interest here is not some units associated with the original variable. The unit of interest here is standard deviation, okay? So you would do the interpretation as any variables that we've learned in the past, but the unit changes to standard deviation. Okay, so again, what does beta 1 b1 hat indicate? So b1 hat indicate the changes in y if x1 increases by 1 standard deviation. Okay, I'm going to stop here for the beta coefficient. Any questions on the concept and the idea before I move into Stata to provide you with an example? Okay, so what I need you to do is just go back to the previous regression and then do it for all the variables in the model, and then you can see the final equation as the following, where the b hat j is called the standard coefficient, which is a ratio between the variance of xj and the standard deviation of xj and then the standard deviation of y multiplied by the estimated beta hat j. Okay. All right. And so before I move to the next topic, I'm going to provide you with an illustration of beta coefficient regression. So beta regression, standardized regression in Stata. Okay. And so for this purpose, so for this purpose, what I'm going to do is I'm going to open up a particular data. It's called the house price data. Okay, so house price to data. Let me find it out. Let me find it, and then let me pull it up. Okay, and so this is the house price data. So what do we see in the data? So basically, we have the price of the data. We have actually the crimes committed per capita. So this provides you with an illustration on the crime rate in the region. We also have the nitrogen concentration, which is parts per 100 million. So this particular variable is a measure of air pollution in the community. Okay, so the higher the nitrogen oxide in the air, then the higher the pollution. Okay, and we also have other variables such as the number of rooms, the distance, the weighted distance to the 5 employment centers. We have access, to radial highways, and we also have property tax per $1,000 of house price. Okay. All right. So what we're going to do is initially we're going to do a regression on price, and then nitrogen oxide, crime rate, and then the number of rooms, distance, and then student-teacher ratio. This is basically an indicator of school quality in the region. And then we also run the robust option to control for general form of heteroscedasticity in the data. Okay, and so we get the regression. Okay, now when we take a look at the estimated coefficient, it's not very straightforward to interpret the estimated coefficient of negative 2,706. Okay, because we have a different unit for price, we also have a different unit for the nitrogen oxide concentration. Okay, the interpretation of the coefficient for the crime is also not straightforward, because the crime variable is the number of crime per 100 population. On the left hand side we have the house price, so it's not very straightforward. And so what do we need to do? So what we need to do is actually we do what's called a loop. Okay, and so by using loop, then we're going to do the same set of operations for the same variable. Okay, why do we need loops? So for example, we need to change the price, we need to change the NOx, crime, rooms, distance, and the student-teacher ratio, and then we're going to standardize the variables. We can standardize one particular variable. So in this case, I'm going to create a new variable, which is called Z price, which is the standardized price. So here I'm using generate instead of, I'm using e-generate instead of just generate, because by using e-generate, then you can use a lot of built-in functions. In this particular case is standardization. Okay, I'm going to, in the do file label the variable, the standardized value of price, but I'm not going to do it in this particular instance. Okay, what I'm going to do is, instead of doing it one by one, I'm going to run a loop for all the variables. Okay, so you can take a look at the loops, and then basically from the loops you generate all these variables: Z NOx, Z crime, Z rooms, Z distance, and Z standard student-teacher ratio, just by 3 lines of command instead of 5 or 6 lines of command. So if you have like many variables in your data set, then knowing loop is actually going to improve your working efficiency. Okay, so I invite you to learn about this loop for learning purposes. And so basically I'm going to do the same set of regression, but instead of regressing it on the level variable, I'm going to regress it on the standardized variable. So I have Z NOx, and then Z crime, Z rooms, Z distance, and then Z student-teacher ratio. Okay, and then we can also use the robust option as well. And so before I do the regression, remember that the estimated coefficient is going to indicate the standard deviation change of Y if the X, or the explanatory variable, changes by 1 standard deviation. Okay, so always recall that discussion. Okay, and so we now have, oh, my bad, actually I leave out one particular command. So I'm going to redo the comment here, but recall that I have to drop the constant. Okay, remember in the slide, we don't have a constant on the standardized regression on the standardized variable. Okay, but having the constant is not going to change, and so basically it's not going to affect your estimated coefficient if you accidentally still input the constant. All right. Does anyone wants to provide an interpretation on the estimated coefficient for the nitrogen oxide? Any volunteer? Okay, Pramudio, can you provide an interpretation on the estimated coefficient for the standardized nitrogen oxide? Okay, so Pramudio is not with us. Kayandra, can you provide an interpretation for the nitrogen oxide variable? Okay, so anyone in general?
Can I try, sir?
Sure, go ahead, Stephen.
Oh yeah, so the Xenox coefficient, we can interpret it as an increase of 1% in Xenox is estimated to decrease the dependent variable by 0.34.
Okay, so an increase in the nitrogen oxide concentration in the air by 1 standard deviation is going to increase the house price by 0.34 standard deviation. Okay, and of course, you know, we don't have to say it all the time, but just remember that the interpretation assumes that all factors are held constant. So basically, ceteris paribus. Okay, all right. So I'm going to provide one more opportunity for a student to interpret the estimated coefficient for the standardized crime. Anyone?
Sir, if I may try.
Sure, go ahead.
So from that coefficient, if the crime increases by 1 standard deviation, the house price would decrease by 0.14 standard deviation.
Yes, exactly. Okay, so for every standard deviation increase in the crime rate in the area, house prices decreases by 0.14 standard deviation, ceteris paribus. Okay, so all else held constant. Okay, very good. So in this particular regression, then the only positive estimated coefficient is for the number of rooms. Okay, the distance, so the further the distance to the city center or in area where the standard student teacher ratio is relatively high, which indicates that the school quality is lower, then we're going to have lower house prices as well. Okay. All right, so very good. So that's the interpretation of Vera coefficients. So if you feel that, you know, it's going to be quite difficult for you to do the interpretation of the variables used in the regression model, then one particular solution is to use standardized variables. However, if you use standardized variables, you have to be quite careful in terms of interpretation, okay? Why? Because the unit is no longer the level unit that you use in the original variable, but you actually now use standard deviation as the unit. Okay, good. I'm going to go back to the slide, and again, we're going to revisit Stata in several slides, okay? So the next point of discussion is interaction terms. So interaction terms are actually very common in regression models. So the interaction terms actually going to provide an illustration on whether or not the estimated coefficient change if other variable, the value of other variable change, okay? So again, it may seem quite abstract at this point. And so we're gonna go and then look at a particular example so that you can have a general view on the use of interaction terms, okay? All right, so let's start with the first discussion. So in many applications, the partial effect of a variable depends on the value of another explanatory variable. Okay, so for example, when we estimate the return to college education. So what is the return to college education? So in the data, the majority of individuals in a particular country, for example, in Indonesia, holds high school diploma. Okay, so basically they graduate from high school. However, we also see a non-negligible proportion of individuals in Indonesia who actually go on to college, to university, and then obtain university or college diploma. So what we want to know is that whether or not there is a financial return in getting this college education. Okay, why is this quite important? Well, when you go to college or when you obtain higher education, then there are some costs associated, with going to university. So it's the tuition that you pay, it's the stipend that you pay, also the opportunity costs. Why? Because if you do not go to university, or if you do not go to college, then you could have work. Okay, but at the same time, you also face benefits in going to college. Okay, so you're more productive, and then you're going to be able to signal to the employer that you're a higher ability worker or a high productivity worker, and so you may obtain higher wage from the potential workers. Okay, and so what labor economists and then education economists and those interested in gender in the past few years, they wanted to know whether or not the return to college education actually differ by gender. Okay, so we're interested in looking whether or not the return to college is equal across the gender or whether or not they're different. Okay, so that's something that we're interested in. Another interesting line of research is whether or not the return to schooling is different by school quality. Okay, so for example, if you go to a particular university, okay, we'll going to that particular university. So assume that it's a better quality university, is going to provide you with a higher return to schooling. And compared to when you go to a lower quality school. Okay, so for example, another example is that you compare two individuals. One went on and enrolled in higher quality university, and the other one enrolled in low quality university. Okay, so we'd like to know whether or not the return to schooling actually differ by these two individuals. Okay, so if we'd like to know whether or not the return to schooling actually differ by school quality, what we can do is we can interact between education and quality. So what I mean by interact is that I create a new variable, and the new variable is actually the interaction between education and quality. And then I use the interacted variable into the regression model. Okay, so that's going to be interaction. Now notice here is that the variables that I use for the interaction term is assumed to be at least an ordinal or a continuous variable. Okay, so remember, if you have the level of measurement, you have the categorical variable, you have the ordinal variable, you have the interval variable, and you have the ratio variable. So when I do this interaction, I'm using two kind of like ordinal variables. Okay, so in chapter 7, if I'm not mistaken, we're going to learn about interaction terms using dummy variables. Okay, but that's for I guess 2 weeks from now. We're going to focus here on second. Okay, so again, what we're interested in any regression is to know the partial effect of a particular variable. Okay, suppose that you'd like to know how wages change by years of schooling. And so what you do is that you take the partial wage divided by the partial education, then what you get is that it's simple, mathematics. I'm hoping that everyone will be able to get it. So if you take the first, the first order with respect to education, then you'll get beta 1. Okay, education with respect to education is just 1. And then for this one, the first order with respect to education, or the first derivative with respect to education, is going to be beta 3 quality. Okay, and so the change in the return to education, or the change in wage as education changes, is going to be beta 1 plus beta 3 times quality. Okay, so we're going to assume that beta 3 is positive. So the return to schooling of an individual who went to better quality school is higher. Okay, so that's going to be the test that we're going to be looking at. However, let's take a look at beta 1. Okay, what is the interpretation of beta 1? So the interpretation of beta 1 is going to be the effect of schooling on wage for school with 0 quality. Okay, so suppose that this quality is equal to 0. Okay, then basically this is 0 as well. And so the partial effect beta 1 illustrates the effect of schooling for those with 0 quality of school. Now, of course, we're not interested in evaluating the partial effect of schooling for people with 0 quality. Okay, so this is the issue. Now I'm going to provide you with another illustration. So consider the same model, but what I'm going to do here, I'm going to take the derivative with respect to quality. So we'd like to know whether or not the effect of school quality increases by years of education. Okay, so there's kind of like a complementary effects of education on school quality. Okay, so what is the interpretation of beta 2? Anyone? So if you pay attention to the previous the previous one, which is the derivative of wage on quality, what is the interpretation of beta 2 right here?
May I, sir?
Yes, go ahead, Saki.
I think since now we're interested in the returns to quality, I think the interpretation of B2 is the quality of schools or university. If no one has spent no years in education, but I don't think that is possible, because you cannot go to university, but or you cannot go to school, but you do not accumulate years in education. So I think that is the interpretation.
Okay, all right, so very good, you're going into the right direction. I'm just going to polish it just a little bit. So what we're interested here is to see, again, very good, the return to quality. Okay, however, beta 2 actually suggests the return to quality among who? Among individuals with 0 level of education. Okay, and so individuals do not go to school, they don't have any education, but at the same time, we also do not observe quality. So basically, again, we're not interested in the effect of quality among individuals who do not go to school. Okay, so this is going to be a problem if you just run a regression of education, quality, and the interaction of education and quality in general. The interpretation of beta 1 and the interpretation of beta 2 straight out of the regression output is not going to be informative. Okay, what do we need to do? Well, there is a solution for that, and this is going to be the solution that we care about. Okay, again, just to go back to the original equation, suppose that we have a general equation where we regress the dependent variable y on variable x, variable z, and then an interaction term of x and z. Okay, so we're interested in the marginal effect x on y, and we can see that the marginal effect of x on y depends on the value of z. Okay, so depends on whether or not beta 3 is higher than 0 or positive, or it really depends on whether or not beta 3 is negative. Okay, so suppose that beta 3 is positive, then the marginal effect of x is going to increase with the value of z. What would happen if the estimated beta 3 is actually negative? If the estimated beta 3 is negative, then the marginal effect of x on y decreases with the value of z. Okay, so that's going to be the marginal effect. Again, this is not the estimation that we care about. Why? Because beta 1 illustrates the effect of x on y for z equals to 0. It's something that's not interesting. In a similar manner, beta 2 actually indicates the marginal effect of z on y when x is equal to 0. Okay. So the solution is called centering. Okay. So what is centering? Centering is basically you subtract the observed variable on the mean. Okay. So this is quite different with standardization. Okay. So remember, in standardization, what you do was that you subtract x with the mean and then divide it by the standard deviation of that variable x. Okay. So in centering, we don't do division by the standard deviation. So what we do is just subtract the variable with the mean. Okay, and then we're going to denote the centered variable as xc. Okay, and we're going to do that for all the variables. So in this particular case, I'm also going to center the z variable. So z centered is just z minus z bar, okay, which is the average value of z. Okay, and then we're going to do an interaction term between xc and then zc as well. So very straightforward. Okay, now what does this centering do to our regression? Okay, so long story short, the transformation that we did for the x variable as well as for the z variable, indeed it's going to change the estimated coefficient. Okay, so the coefficients that you will obtain from this regression is going to be quite different with the regression excuse me, with the estimated coefficient obtained from this regression. So they're going to be quite different. Excuse me, I'm going to drink some water first. Okay, as you can see that the parameters of the model is different. Here we use the betas, here we use the gammas. Okay, so this indicates that the estimated coefficients will be different in these two models. Okay, all right, so I'm going to go into the detail in the next section. Again, I don't want to kind of like scare you with mathematics, but it's just a very simple mathematics. It just look quite long, okay, but it's very straightforward. Okay, so as you can see, again, xc, zc, and then xc, zc is actually just centered x and centered z, and interaction between centered x and centered z. So there's nothing to be, concerned about. And so what we're going to do is just we're going to do multiplication based on the variables that we have. And so we have y equals to the constant. So this is going to be a constant. And in the original variable, this is just the constant. Okay. And so basically, the transformation that we did for x, z, and then the interaction of x and z does not change the equation. It's just change the number and the interpretation. Okay. And then this one is going to be beta 1. So, or it's equivalent to beta 1. And then this is equivalent to beta 2. okay? And then the variable that we're interested in, which is the interaction variable, is actually just the same, okay? So beta 3 and gamma 3 is going to be the same. Now, the good thing about the interaction is going to be the interpretation, okay? And so in this slide, we've established that the transformation that we did does not affect the model in terms of the qualitative result. So they're going to be the same parameters. However, the interpretation is going to be quite different. Okay, so again, what we're going to do is we're going to do the interpretation. So what is the interpretation of gamma 1? So gamma 1 is the parameter associated with xc, the center x. And so gamma 1 captures the marginal effect of a unit increase in x when z is at its mean. Okay. All right. So I'm going to compare between the interpretation of beta 1 and then the interpretation of gamma 1. So what is the interpretation of beta 1? So the interpretation of beta 1 is the marginal effect of a unit increase in x on y when z is equal to 0. That's the interpretation of beta 1. What about the interpretation of gamma 1? The interpretation of gamma 1 is the marginal effect of a unit increase in x when z is at its mean. Okay. So going back to the education and then the school quality example, then the associated coefficient with education is going to provide you with the following interpretation. It's the marginal effect of a unit increase in education when school quality is at its mean. So basically, we're identifying the return to education for individuals who attended school with average quality. Okay. The same goes with the difference in the interpretation between beta 2 as well as gamma 2. So what's the interpretation of beta 2? The interpretation of beta 2 is the marginal effect of a unit increase in z when x is equal to 0. What about gamma 2? So gamma 2 is going to be the marginal effect of a unit increase in z when x is equal to its mean. Okay. And when we go back to the school quality example, then the interpretation of the estimated coefficient associated with school quality is going to be the marginal effect of a unit increase in school quality for individuals with average schooling. Okay. So this is the interpretation of the regression using interaction terms. It's going to be more straightforward. It's going to allow us to better interpret the data as well as the result. Okay. All right. So don't worry if from this presentation it doesn't seem quite clear or it doesn't seem quite intuitive as yet. That's okay. It's going to take probably a couple of sittings to really understand this, but hopefully this is going to be quite useful. All right, so before I go to Stata and discuss the concept, any questions? Anything technicals that you like to know, or anything technicals that you'd like me to repeat, or anything conceptual in terms of the interpretation and so on? Feel free.
Excuse me, sir?
Sure, go ahead.
I didn't quite understand when you were explaining about the interpretation of beta 1. Beta 2. Could you re-explain that?
Okay, sure. So I'm going to go back a couple of slides. So I'm going to provide a discussion on the interpretation of beta 2, and then I'm going to contrast it with the interpretation of gamma 2. Okay, so beta 2 is the estimated coefficient associated with the variable z, and then gamma 2 is going to be the estimated coefficient or the parameter associated with the centered z. So beta 2 is going to be the marginal effect of a unit increase in z when x is equal to 0. Okay, so that's the interpretation of beta 2. What about the interpretation of gamma 2? So the interpretation of gamma 2 is the marginal effect of a unit increase in z when x is at its mean. Okay, and so suppose that this is education centered and this is quality centered, then the estimated gamma 2 is going to provide us with the intuition of the marginal effect of a unit increase in quality for individuals with average education. So that would be the interpretation of beta 2 and the interpretation of gamma 2. Okay. All right. Any other clarification before we go to Stata and discuss a particular example? All right, great. So I'm going to go to Stata and we're going to discuss an example on the use of interaction term for regression. Okay. Okay, so I'm going to do regression based on the data at 10. So this is one of the data that we have in the Wooldridge dataset repository. And then what are the variables in the dataset? What we're interested in is going to be the standardized final test score. So basically, this is the standardized test score for the the dependent variable that we're interested in. And so what we're interested in is we're interested in the regression of test score on prior GPA, the squared of prior GPA, and then attendance rate, interaction between attendance rate and prior GPA, as well as ACT and ACT score, squared of ACT score. Okay, so let's do the regression, and I'm going to ask you to pay a bit of attention because what I'm going to do is I'm going to do a bit of regression that you haven't seen before. So here I'm going to use standardized final as the dependent variable. I'm going to use prior GPA as one of the explanatory variable. Now I'm using C dot to indicate to Stata that prior GPA is a continuous variable. Okay. Now I'm going to do a double hashtag. So double hashtag means that I'm going to regress standardized final on prior GPA and then prior GPA multiplied by prior GPA. So basically it's prior GPA and then squared of prior GPA. I'm also going to regress it on attendance rate and then the interaction between prior GPA as well as attendance rate. Okay. And then lastly, I'm going to regress it on ACT as well as ACT squared. And also I'm going to do robust option to control for general form of heteroscedasticity. Any questions from here before I go and run the regression? All right, so let me clarify. So I'm regressing the standardized final test score on prior GPA and then square of prior GPA, and then attendance rate and the interaction between the attendance rate as well as prior GPA. I also regress it on ACT and then square of ACT, and I'm using robust to control for general form of heteroscedasticity. Okay, and let's do run. And so this is the result of the regression. Okay, so I'd like to have everyone pay attention on this estimated coefficient for the attendance rate. Okay, what is the estimated coefficient? So the estimated coefficient is going to be the marginal effect of an increase in the attendance rate on final test score when or among individuals with zero prior GPA. Okay, so this is the interpretation. Okay, again, the interpretation on the estimated coefficient for attendance rate is the marginal effect of unit increase in attendance rate among individuals with zero prior GPA. Again, that's not something that we're interested in. Any questions before I go and then provide you with, on how to do the centering? Okay. So what we need to do is basically we need to do a centering for the variables that we're interested in, particularly variables that we interact. Okay. So in this particular case, we interact prior GPA with attendance rate. And so at least we want to center prior GPA and we want to center attendance rate. Okay. And then let's do loop. And so for each variable, prior GPA and attendance rate that I stored in local called myvar, I'm going to run through the following command. First, you take the sum of the variable and then obtain the mean. And then what you're going to do is create a new variable with, with C in front. And then it's going to be defined as the value of the variable minus the mean. Okay, and then I'm going to label it as centered the variable that we're interested in. Okay, so this is how you do it, and then again you can do it in independently so that you have an idea on what's a loop and then what it's used for. Okay, so I'm going to do the same regression here, but I have a tweak. So basically, instead of using prior GPA, I'm going to use centered prior GPA. Okay, instead of using attendance rate, I'm going to use centered attendance rate. Okay, so I don't interact ACT except by itself, so I'm not going to do a centering in this particular case. Okay, and then I do the regression. All right, so let me ask you to pay attention to the estimated coefficient. In this particular case, the estimated coefficient is actually positive. Now I'm going to go back to the previous regression. In the previous regression, the estimated coefficient is actually negative. Okay, why? Again, this is the estimated marginal effect of an increase in attendance rate among people with zero prior GPA. Again, something that we're not interested in. However, in this particular regression, the interpretation of the coefficient is going to be the marginal effect of an increase in attendance rate for individuals with average prior GPA. Okay, so that's going to be the interpretation. So similarly, what is the interpretation of the estimated coefficient for prior GPA? So the interpretation is, this is the marginal effect of the unit increase in prior GPA for individuals with average attendance rate. However, the interpretation is a bit difficult. Why? Because we also see the effect of the squared prior GPA. Okay, so it's not as straightforward as that. But let's go and see. We can do some graphic and then to see the marginal effect of prior GPA for different value of attendance rate. Okay, and so I'm going to introduce you to what's called the margins command. So the margins command is going to allow you to calculate the marginal effect of prior GPA for different values of attendance rate. Okay, and so basically this is going to be the estimated marginal effect of prior GPA for different value of attendance rate. Okay, which is quite useful in the case of regression with interaction term. And we're also going to be able to run the plot. Okay, so I'm going to share you the plot to provide a better understanding of the effect. So here we're going to see the effect of the marginal effects of prior GPA. And so that's going to be on the vertical axis. And this is going to be the centered attendance rate. What does it show? It shows that the effects of prior GPA on standardized final test score actually differed by attendance rate. In particular, individuals with higher attendance rate tends to have higher effect of prior GPA. Okay, so if you're a good student and you have a strong academic record, then by attending classes and paying attention to the classes, the effect of that previous accumulated knowledge is going to be higher. Okay, so this is what's called the complementary effect of attendance rate on current knowledge. All right, any questions before I go to the next order of discussion? Go ahead.
Sir?
Yes.
When do we know when two variables interact and we have to incorporate the interaction terms into the model?
One is usually based on the theory. Okay. Second, it could be based on some academic curiosity that is backed up by a particular, anecdotal findings or, prior empirical studies. Okay, so basically, it's just not out of the blue, but it's usually started from, some literature review or some theoretical consideration. Okay. And if you find such argument for interaction variables, then it's always good to do empirical tests on the interaction variable. Okay, so it may not always the case that the interaction variable is significant or it has an effect, but it's always good to do the interaction term. Okay, if the theory or the previous studies say so. Okay, good. Any other clarification, questions? Okay, I understand that the regression that I just did in Stata is not straightforward. However, again, it's going to be a function of everyone independently reviewing the study materials and then the Stata codes to understand what's the interpretation of the coefficients, what's the interpretation of a particular syntax used in Stata, and then what's the interpretation of the graphics. Okay, these are quite useful. Whatever or whichever the department that you're from, whether you're a business student or whether you're economics students, then knowing what interaction terms mean and then knowing what's the effect of standardized variable or the meaning of centering is going to be helpful in your future research. Okay, so basically you're accumulating as much as ammo or a different ammo for your eventual regression. Okay, so that's going to be on interaction terms. Unless there is a question or a clarification, I'm going to go back to the slide and discuss polynomials. Good. Okay. So let me go back to the chapter and let's discuss the chapter. Okay. So now we're going to discuss what's called polynomials. Okay. So polynomials is basically a function that could accommodate nonlinear relationship between two variables of interest. Okay, suppose that we have wages on the left-hand side and we have years of working experience. When you first enter the labor market, then the effect of experience is going to be quite high. Okay, and then as you work in a particular job, the effect of working experience is going to flatten out after several years and eventually it's going to decrease. Okay, and so it also reflects the fact that when you first enter the job, additional year improve your productivity by a lot, up to a certain years of working experience, and then beyond that, your productivity actually decreases. This is something that we observe commonly in the data. It's very interesting, and we're going to see, how we deal with the presence of nonlinear relationships, and then how we go about it in Stata. Again, nonlinear relationship between variables are actually the norm rather than the exception. So one way to capture these is by allowing variables to enter as polynomials. So here we're not limiting the relationship to just be a quadratic relationship. It could be a polynomial to the degree of 3 relationship. It could be the polynomial of degree 4 relationship. So we're not limiting to just polynomial of degree 2 or quadratic relationship. Okay. So the Goff-Marquez assumptions specify that the model must be linear in parameters. So basically your beta 0, your beta 1, beta 2, beta 3, beta 4, and beta 5, and so on needs to be linear. However, nonlinear transformations of variables are actually okay. So for example, for any variable xk, we can actually include xk square, and then xk to the power of 3. We can also include xk to the power of 4 and to the power of 5. Now the big question is, how far should we go? Okay, so what's the ideal polynomial degree that we like to incorporate into the model? That's not something that we can decide, before we do the actual regression. That's actually an empirical question. Okay, so ideally what you want to do is just test out different specifications. So for example, what if you just include a quadratic function? What if you also include a polynomial to the degree of 3, a polynomial of degree 4, and so on? And you want to see whether or not addition of the degree in the polynomials actually provide you with a better explanatory, better explanatory power of the model that you estimate. So that's probably the best way to say it. Again, we're not going to be able to tell what's the optimal polynomial degree, but it's rather an empirical question that you like to check. Okay, so again, what is going to be the polynomial is going to allow the change in average y associated with different x to depend on the level of x itself. Okay, so the effect of a change in x can rise or fall with the level of x. So x could have a decreasing or increasing partial effect depending on the estimated coefficient of the model. Okay, again, it's not going to be clear at this moment whether or not a model in general will have a decreasing or increasing partial effect. It's really going to depend on the estimated coefficient. Okay, so one example that we're interested in, as I've said in the previous slide, is the marginal difference in wages to an extra year of experience should decline with total years of experience. Okay, so if you look at the data, okay, so I'm gonna just briefly provide you with the illustration. So suppose that this is the years of working experience, and then this is the wages. Okay, so if you look at the data early on, as experience increases, then average wage goes up, and then after some certain point, the return is actually negative. Okay, this means that you have negative outcome afterwards. Okay. All right. So this is an example where we want to capture non-linear relationship between the left-hand side variable, in this case wages, and experience on the right-hand side variable. Okay. Again, what I'm illustrating here is just the relationship between two variables, but in general, again, there are other variables that we need to take into account for in the regression. All right, so I'm going to start with a very simple quadratic function, and then you can go on and independently learn what happens if we have a regression with a polynomial of degree 3, or what happens in a regression if I have polynomial of degree 4. I'm going to start with a polynomial of degree 2 or the quadratic function. So what we're interested in is what's the marginal effect of x on y. Okay, so if x changes by 1 unit, what would happen to y? So here it's clear that the first derivative of y on x is going to be beta 1, and then 2 times beta 2 multiplied by x. So this is basically the partial effect of x on y. Now, as you can see, it really depends on the value of beta 2. So beta 2 could be positive. What does it mean if beta 2 is positive? It means that the partial effect of x is actually increasing with x. So the higher the x, the higher the marginal effect on y. What would happen if beta 2 is actually negative? If beta 2 is negative, then the effect of x on y is actually decreasing with x. So the higher the x, the lower the effect of x on y. Okay, so this is what's called the increasing partial effect or decreasing partial effect of x, as mentioned in the past couple of slides. Okay, and as you can see that the rate of change of x is going to be a constant, which is 2 times beta 2. Okay, I'm going to stop here and take questions or clarifications. Any? All right, that's good. So again, I want to provide you with a short summary so far on the polynomial. So basically, we can include nonlinear relationship in our model. So we can have a quadratic function, which is a polynomial of degree 2. We can also have polynomial of degree 3, and we can have polynomial of degree 4. Okay, and what we're interested in is actually to understand whether or not there is an increasing partial effect or whether there is a decreasing partial effect with respect to the variable itself. Okay, so it really depends on the estimated coefficient. For some coefficients, we're going to get an increasing partial effect of the change in the variable itself. We could have a decreasing partial effect for other cases. Okay. All right, so this is going to be the example that I'm going to discuss. I'm going to provide you with the illustration here first, and then we're going to go to Stata. Okay, so suppose that we regress wage on experience and the square of experience. Again, you can also include other explanatory variables, but for this particular case, I'm going to just provide you with experience and then the square of experience. So what can you see? The estimated beta 1 is positive. So it means that, when you first enter the job, then the return to experience is going to be positive, which is good. What's interesting here is that the estimated beta 2 is actually negative. What does it mean? It means that as you accumulate experience, the return to experience actually decreases over time. Okay. In other words, there is a decreasing partial effect of experience on wages. Okay. Now, suppose that we have someone who works for 10 years. Okay. So what's going to be the return or the marginal effect of experience for someone with 10 years of working experience? And so basically it's just 0.298 minus 2 times 0.061 times 10. Okay, and that's going to indicate the experience, the effect of experience on wages for someone who's worked 10 years in the labor market. Okay, and so basically, from this illustration, we can calculate that the first year of experience increases the wage by about 0.30 unit of dollar. And then the second year is going to increase it by 0.29. So as you can see, the estimated effect from the first year and the estimated effect of education on and the experience on the second year is actually lower. Okay, so it has a decreasing trend. You can see that in the Stata regression, which I'm going to show you after this. Okay. Just one last thought. If you recall your calculus, then you're going to be able to identify the wage maximum with respect to work experience. Okay, and so basically you can identify the value of experience such that wage is at its optimum. How do you do it? Well, you take the first order, and the first order has to be equal to 0. Okay, so if I go back to a slide, this is the first order basically, and you have to equal to 0. Okay, and then if you do the regression, then the maximum wage with respect to work experience is going to be on the 25th year. So your return to experience is going to be basically positive until year 25. And then after that, one more year of experience actually provides you with negative effect on wages. Okay, why? Because you're less productive or for many reasons. Okay, any questions before I go and discuss the example in Stata? All right, so for the discussion in Stata, I'm going to use the data set called wage1. Okay. So wage1 is a data set that contains the following. Wait, let me reshare. My apology. I'm going to share the second desktop. Okay. So I'm going to use wage1 data. And what does wage1 data consist of? It consists of a lot of variables. You have wage, and then you have the log transform of wage. You have education, experience, tenure, and then all the characteristics that we're interested in. Okay, so what I'm interested in is to see whether there is a nonlinear relationship between wages and experience. Okay, so to do that, what I'm going to do is I'm going to create a two-way graph, and I'm going to use scatter wage and then experience, and then I'm going to do quadratic fit of log wage and experience. Okay, and then I'm just going to do this option to provide you with a better view of the result. Okay, so this is going to be the plot of years of experience on the x-axis, and then wages or log wages on the y-axis. As you can see, the quadratic fit provides you with an illustration that as you increases years of experience, wages is going to increase up to a certain point, and then after that it's actually going to decrease. Okay, and so this is right at about 24 or 25 years of working experience. So basically the maximum wage that you'll get is going to be on average, again, is after you work for 25 years. And after that, the effect is actually going to decrease. Okay. Now, let's put this into regression so that we can better understand what's the effect. So there's a lot of variables involved here. So it's going to take some time for me to write it. And so I'm just going to copy what I've written so far. Okay. So basically, you're going to regress log of wage on education, on experience, and then the squared of experience. And so I'm going to declare to Stata that experience is basically a continuous variable, and then c.expr double hashtag c.expr means that I'm going to regress log wage on experience and then the square of experience. And then I have all the other control variables in the model, and I'm going to use the robust option to control for general form of heteroscedasticity. Okay, oops, actually I cannot do that, so I have to get rid of this. Basically, just going to do this. Okay, now before I do the interpretation of experience, does anyone wants to help and interpret the estimated coefficient for education? So what's the estimated, what's the interpretation of the estimated coefficient for education? Remember, we have log of wages on the left-hand side. Anyone recall how to interpret the estimated coefficient for a variable when the left-hand side variable is log transform? Okay, so okay, you can recall it from chapter 3 discussion, chapter 2 basically. So the estimated coefficient suggests that additional year of schooling is associated with higher wages by about 4.76%. Ceteris paribus, all else constant. Okay. Another interesting aspect is that the estimated coefficient for the experience variable is positive. However, the estimated coefficient for the squared experience is negative. Okay. The question is, are the experience variable and then the squared experience variable statistically significant or not? Can anyone tell from the regression result whether those variables are significant or not?
I think at 5%, it is statistically significant.
Yes, so both the experience as well as the squared experience variables, they're both statistically significant. Okay, you know, you can evaluate it from the t-statistics. They're all larger than 2 or lower than -2, which is the rule of thumb if you have alpha of 5%. Okay, it's actually higher than the 2.56 and lower than -0.256, which is the critical value for alpha equals to 1%. Okay. Another way of looking at it is to look at the p-value. The p-value here is lower than 0.05. It's even lower than 0.01. In fact, it's even lower than 0.001. Okay. It means that both the experience and then the squared experience variables are statistically significant. What about the confidence interval? Do you see 0 within this confidence interval? The answer is no. Since 0 is not on the 95 confidence interval, then we can reject the null hypothesis that the estimated coefficient is equal to 0. Okay, and so the t-statistics, the p-values, as well as the 95% confidence intervals all say that there is a significant effect of experience and then squared experience. So basically, you know, in the early life of your working experience, your wages increases up to some point, and then it's going to decrease. Okay. So the good thing about Stata is that it allows you to you know, estimate the marginal effects for different values of experience. So I'm going to run this. Okay. So what I did was that I summarized the experience, and then I can observe that there are individuals who just work for a year. And then the largest is individuals who've worked for 51 years, okay? And so what I'm going to do is basically estimate the marginal effect of experience when individuals have different years of experience. So basically, I'm estimating the marginal effect of experience when someone has been working for a year to individuals who's been working for 51 years. Now, as you can see, the estimated effect for individuals who's been working for, for the early years is going to be positive until year 26, and then additional year of working beyond the 26th year is actually negative, okay? What's cool about Stata is that you can also do a margins plot, okay? So what does the margin plots tell you? Okay, so the margin plots tell you basically this is the estimated effect of experience is actually decreasing. So the slope of this line is actually 2 beta 2, okay? How do I know? This is the second order derivative of y with respect to experience, okay? You can check it in the slide to know that this is actually 2 times beta 2, okay? Another example, interesting thing is that after the 26th year, okay, so this is 26th year. After 26th year, then the estimated effect of experience is actually going to be negative, okay? So this is the illustration of the marginal effects. And what does this black shadowy line tells you? This black shadowy line tells you the confidence interval for the estimate. Why do we have a wider confidence interval right here? Right here, and we have a relatively narrow confidence interval. We have a relatively narrow confidence interval in the middle because we observe a lot of observations in the middle. And so if you have a lot of observation, your standard error decreases and your confidence interval shrunk. However, in the far left or the far right of years of experience distribution, there is a smaller number of observations, and because there is a smaller number of observation, the standard error is larger, and so the confidence interval is relatively wider. Okay, so this is an estimated effect of experience for different years of experience. Okay, so this is something for you guys to learn independently, and there's a lot of interesting things that you can actually do with these margins, as well as the margins plot command in Stata. Okay, so very useful. Okay, I'm going to take questions before I discuss goodness of fit and then prediction and residual analysis. Go ahead. Okay, so if there is no question, I'm just going to do a simple discussion on the regression. Okay, so let's focus on this regression. Okay, and then I'm going to regress it on more complex multilinear regression, multiple linear regression model. Okay, so in particular, I'm going to regress log wage with education, experience, score of experience, and so on and so forth. What I want you to do is pay attention on the R square. Okay. All right. And so in the initial regression, the R square is about 0.1858. What does it tell you? So 18% of all variance in the data can be explained by variance of the model. Okay, and the remaining can be explained by the variance of variables that we do not observe. And so what do we do after we obtain explanatory variables? After we add explanatory variables, then R square actually increases. Okay, and so previously the R-square is just 0.1858. It's now 0.5289. And so basically about half of the variation of the actual data can be explained by the variation into the model. And so basically adding explanatory variables will actually improve the R-square, okay? But again, just to be very careful, a high R-square does not imply that there is a causal interpretation, okay? Now, another thing is that a low R-square does not preclude precise estimation of the partial effects. Now, just one thing that I like to highlight is that in regression with robust standard error, we may not be able to obtain the adjusted R-square. So I'm going to do another regression. However, I'm not going to use the robust option, okay? So when I leave out the robust option, I'm going to get a regression result that provide you with adjusted R-square. So what is adjusted R-square? So basically, if you add explanatory variable into the model, your R-square increases automatically, okay? However, R-square does not impose a penalty for adding new regressors, okay? So for example, if you add a regressor that is not relevant in terms of explaining the dependent variable, then the adjusted R-square is actually going to adjust for that, okay? So basically the adjusted R-square increases if and only if the t-statistic of a newly added regressor is greater than 1 in absolute value, okay? In fact, it could also take negative value, okay? And so in this case, the adjusted R-square is very, very close to the R-square. What does it mean? It means that most of the explanatory variables, if not all the explanatory variables that we have in the current model, are actually relevant explanatory variables, okay? And as we have seen in the previous lecture, even though some variables are not statistically significant, then it means we should throw them out of the regression model. Not necessarily. Why? Because there could be some collinearity between the explanatory variables of interest, and the multicollinearity increases the standard error, decreases the t-statistics, and so we fail to reject the null hypothesis, okay? It doesn't mean that the variables, it's not significant in the population. It's just that the current model actually estimate that, otherwise, okay? We can also see that some of these variables are not significant, but perhaps taken together, they could be significant. Okay, so basically, this is going to be some of the, reason why we want to include, additional variables into the regression model. In the initial regression, the root mean square error is 0.48. However, after you include regression variables, then your root mean square error decreases to just 0.37. And so basically, if you add additional regression variable, it could reduce the error, and then it could improve the precision of the estimate. And so you're more likely now to reject the null hypothesis when the null hypothesis is false, okay? So that's the idea of adding regressors to reduce the error variance, okay? All right, so that's a very quick explanation on R-square as well as adjusted R-square. Any questions? Okay, all right. So that's going to be the discussion of goodness of fit. Again, goodness of fit does not tell you anything about causality. goodness of it tells you whether or not the model that you have will allow you to explain some of the variation of the model, some of the variation of the data. Basically, it's an indicator of whether or not it's a good predictor of the data or not, okay? It doesn't tell you anything about causality. So be very careful about boasting about R-square, okay? In some regression, unfortunately, even though you include a lot of important variables, it's just very difficult to control for. Okay, I'm going to go back to the slide and I'm going to discuss the remaining topics, which is on prediction and residual analysis. Okay, so far, we estimated the coefficients, and then given the coefficients, we can actually predict the value of the dependent variable. Suppose that we observe individual with college education who's worked for 20 years, and then who is a male, who is married with 2 children, who lives in the West, and works in the manufacturing sector as a manager, for example. Given those information and the estimated coefficients taken from the regression, we can actually predict the wage of the individual, okay? It's not going to be the precise wage, but it's the wage predicted by the model. Now, when we do prediction, we also want to take into account some uncertainty. So where do the uncertainty comes from? Well, the uncertainty comes from the fact that you obtain sample from the population, okay? So when you obtain a sample from the population and conduct an estimation, the estimated coefficients could be different when you take another sample from the population. And the estimated coefficient for the sample that you take will all actually be different with the sample that you get randomly from the data. So what does it mean? It means that there is some uncertainty about the true prediction. And so what we want to do is we want to incorporate some of that uncertainty into the model by using confidence interval. Okay, so if you recall from the statistics 1 and the statistics 2 class, not only that we're interested in the point estimate, we're also interested in the interval estimate. Okay, so that's something that we're going to discuss. Okay, so again, this is a short version of the multiple linear regression model. You can have k explanatory variables, but for the sake of discussion, I'm just going to show you 2 variables. So we're going to impute the values of the independent variables. So what's the predicted y? For someone with x1 equals to 10, x2 equals to 4, for example. Now we're going to get a prediction for y, which is the estimated value of y, or the expected value of y, given x1 is equal to 10, x2 equals to 4. Okay. Let's make it more general. Suppose that C1 and C2 indicates value of x1 and x2 respectively. Then the parameter that we aim to estimate is theta 0. Okay. And after we obtain the estimation, which is, after we obtain beta 0 hat, beta 1 hat, and beta 2 hat, we have an estimate for the parameter theta 0. So it's very easy to compute in Stata, and I'll show you how to compute the value of the predicted value of theta. But the question is, what if we want to identify uncertainty in the predicted value? How can we do it? And why do we want to do it? Okay. So basically, to accommodate uncertainty in the data, we want to construct a confidence interval for theta 0. And how do we construct a confidence interval? As you recall from the discussion of confidence interval in chapter 4, what we need to do is basically to calculate the standard error. Okay, so basically the confidence interval is going to be the estimated coefficient plus minus some margin of error. Okay, in this case, the margin of error is 2 multiplied by the standard error theta 0 hat. Why do we have 2 here? Recall, if you assume that alpha is 5%. So basically you have a 95% confidence interval and you have a large enough sample, then the rule of thumb for the critical value is 1.96. And if you round it out, it's just 2. Okay. So this is where the 2 comes from. This is the critical value for two-sided tests, and alpha equals to 5%, or basically the confidence interval of 95% confidence interval. So we're going to estimate theta 0 hat given values of Cj, and then we're going to regress the following. Okay. Now, when we do this regression, the estimated theta 0 and the standard error of the estimated theta 0 is going to be estimate of the confidence interval. Okay, so this is just a conceptual note. Again, I do not want you to calculate it manually, but if you like to know the workings or the inners, that's fine. But in theory, this is how you want to obtain an estimate of the prediction and the confidence interval for that prediction. Again, I'm going to provide you with an illustration in Stata so that you'll be able to understand the confidence interval and the predicted value. Okay, so we just discussed the confidence interval. And now what we're going to do is we're going to discuss what's called prediction interval. Okay, so confidence interval and prediction interval is going to be a bit different. Okay, all right. So suppose that we want to construct a prediction interval for y0. And so we have y0, beta 0, beta 1x1 0 plus beta 2x2 0 plus u0. So basically this is just the model. Now we do a regression, we obtain the estimated coefficient, and based on that estimated coefficient, we're going to estimate the value of y. Okay. So basically from our estimate, we're going to get what's called a prediction error. This is what is estimated by the model. This is the actual value that we see. And so E hat is going to provide you with the difference between the actual value and then the estimated value of the model. Let's take the variance of the prediction error. The variance of the prediction error can be decomposed into two parts. Okay, so basically this is the error variance, and then this is going to be the variance in the prediction. Okay, again, so the variance, the prediction error is going to be decomposed into the variance of the predicted value itself, as well as the error variance. Okay, so there are two components on the prediction errors that we can see here. Okay, so there are two sources of variation. The first source of variation is basically the sampling error in y hat and the variance of y hat. And second is the variance of the error in the population sigma square. Again, this is something that we actually don't see. Okay, since we don't see the variance of error in the population, what can we do? Well, because we don't know the variance in the population, we can use the variance of the residual, which is sigma hat square. Okay, and when we take the square root of the variance, we no longer use standard deviation, but we now have standard error. Okay, why? Because we're using the sample variance. Okay, so the classical assumptions imply that beta hat j and u are normally distributed, then E hat is also going to be normally distributed. Okay, so again, there is the standard error of the prediction or the variance in the prediction can be some explained by the sampling error, and some can be explained by the variance of the error in the population. Okay, and so this is called the prediction interval. And so we can calculate the prediction interval by using the following. And so basically we're going to use the predicted y, and then this is the critical value for t alpha equals to 5%, and for a large number of observations, then this is going to be plus minus 2, okay? And then the standard error itself. Okay, so we discussed two concepts. The first one is the confidence interval, and then the second one is the prediction interval. Which one is wider? Is it the prediction interval? Is it the confidence interval? The answer is prediction interval is going to be wider. Why does the prediction interval tend to be wider? Prediction interval tend to be wider because it incorporates two uncertainties. One is uncertainties from the sampling process, and then second is uncertainty of the error itself in the population. And so prediction interval is usually larger than the confidence interval. Okay, so I'm going to stop here for the the presentation, and I'm going to go back to Stata, and I'm going to provide you with an illustration on how to get confidence interval. Okay, so what I'm going to do is I'm going to go back to the data set called attend, and then using the attend data set, then we're going to provide you with an illustration on how to do the graphic as well as the estimation itself. Okay, so I'm going to share the screen for this data. So the first thing that I want to do is I'm going to do a two-way, and then I'm going to use the LFIT CI, which is the linear fit confidence interval. So we have the standardized final test score, and then we're interested to look at the prior GPA. Here, I specify that is the the standard error of the forecast or the standard error of the prediction. Basically, we're going to use this to calculate the prediction, the confidence interval. Okay, and then CI plot, airline, and then I'm going to do some color. You can pick whatever color that you want, but I'm using gray here. And then I'm going to also do the prediction interval as well. So this is the standardized final, and then prior GPA, and then I'm going to use a more solid pattern for the graph. Okay. All right. Just legend off so that it doesn't crowd the state of the graphic. Okay. So as you can see that there are two sets of line. The first one is the sets of lines that is very close to the blue regression line. So the blue one is a regression line. And so if you see the line that is around the blue line, that's going to be called the confidence interval. Okay. And as you can see here, the confidence interval is actually very, very tight. However, the two lines that kind of like embrace the regression line is actually very wide, and that's called the prediction interval. And why is the prediction interval quite wide? Again, it takes into account two sources of uncertainty. The first one is uncertainty from the sampling process, and the second is on the errors, variance in the errors itself. So it tends to be wider. Okay, so that's going to be an illustration of confidence interval versus prediction interval. Okay, so just to give you a very quick background on how to calculate the confidence interval, it's actually very straightforward. So the first thing that I'm going to do is just do the regression first. Okay, after you do the regression, then you're going to tell Stata to predict y hat. Y hat is going to be the predicted y, and then you're going to request Stata to predict the standard error of the linear prediction, and you want to also obtain the standard error of the forecast. So the standard error of the forecast will allow you to calculate the prediction interval, and then the standard error of the linear prediction will allow you to calculate the confidence interval. Okay, and it's very straightforward to calculate the confidence interval. It's just y hat plus minus 1.96, which is the critical value for alpha equals to 5% and a relatively large number of sample multiplied by the standard error of the linear prediction. And to calculate the prediction interval is quite easy. Also, the predicted y plus minus 2 times the standard error of the forecast. Okay, so that's the idea of prediction analysis. So again, why do you want to do this? If you want to make some prediction or if you want to make some forecast, you cannot be too confident to say that, oh, the estimated forecast is going to be this number. Okay, you want to be fair in the sense that you want to provide some picture of uncertainty. Given the expected value and some variance, in the data as well as in the population, the predicted value is around this and this values. Okay, and that's going to be fair in the sense that you don't tell them that it's actually a particular number, but instead just a particular interval. All right, that's the discussion for today. Any questions on prediction analysis? Okay, so you have all the data sets in log. You also have all the 2 files in log. So please take time to review the materials independently to learn them and be able to identify what needed. Okay, what's needed to understand this. In the next meeting, we'll discuss other issues in specification, such as measurement error on the y variable, measurement error on the x variable. We're also going to discuss issues around outliers. In many data sets, we face the issues of outliers, and I think that's going to be important for us to know. All right, I'm going to stop here unless there is any question or clarification for the last time. All right, awesome. I'll see you guys next week on Monday, usual time, 1:30 p.m. until around 3:30, 4 p.m. I hope that everyone will have a good week, and I think we're going to have a long weekend this week. So enjoy. I'll see you guys next week. Bye-bye.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.